Okay, so let's start this next session, last session of the workshop. So this session, I had a plan to do a tutorial that is very similar to the one we just did. It's also a simulation of the decalanin, the stretching, but with a different method, which, in my opinion, is a little bit more modern, a little bit better in terms of scientific scope, and it's also involving one of the most powerful tools that the NAMD code has, which is the collective variables module. So Mohammed talked a little bit about collective variables. And basically, that module allows you to do almost any type of biasing simulation that you can think of. If you think about the example we just did about the decal, and we were pulling or applying a force to one part of the peptide to the one end. By applying a force in one direction, right? But let's say, if you remember the Matt's talk, he was talking about biasing not only a set of atoms in one direction, but also like the whole protein, from going from one conformation, which was open to the inside of the cell, to another conformation that was open up to the outside of the cell. So that is a movement that involves a collective motion of several atoms, several tens of hundreds of atoms that you need to move. And sometimes those movements are not one directional, like in the pooling case, right? Those movements can involve angles or even torsions regarding quaternions, like torsions between two monomers or two parts that are not connected directly, but they are. So, in my opinion, Colvar's collective variables allows you to do much more complicated things, complicated biasings, if you want. And it's a very intuitive and simple way to do it, in my opinion. Not only you can select which atoms to pull or to push or whatever, but you can also select to apply forces to a custom formula that you just come up, for example, that takes as input different parts of the system. So you can say, I just want to apply forces to the X component of some atom, and the angle plus the angle of this atom with another atom. Basically, you can create any combination of atoms, coordinates, and angles, and dihedrals, and whatever you think of. So many, if not all, of the more recent papers, publications done in our group with any type of biasing simulation along with collective variables. I think because it's a very powerful tool. That said, it's a very advanced tool. And I understand that there might be people here that are still struggling with PSF and PDBs. So I think that jumping from what we just did to this next tutorial that is relatively short, that presents you with a very simple case of basically a free energy simulation using biasing, a different flavor of biasing, not SMD. using collective variables is a good transition for everyone. So I propose to do that. We have a little bit less than 2 hours. I don't expect it to take more than half an hour, 45 minutes maximum. So if you are still here after that, we can do another tutorial in a different topic. That might be the parameterization tutorial of the force field toolkit that I explained. We can do that one, or we can do a more a different tutorial, like for example the membrane protein tutorial, which has a little bit of system preparation and different type of simulations, more complete scientific work. So that's up to you. I counted, we have a little bit over 15 participants, maybe a little bit more now. So let's do that. So is there any questions from last session or any session during this tutorial, during this workshop?
Quick question. I just got back and heard half of what you said.
Okay.
Did you say you were going to do an FFTK at some point?
Yes.
Okay, thank you.
So we're gonna do a very short tutorial that is similar to the one we did before for the free energy. And then we're gonna do a few parts of the tutorial, the 50K, if people want to do that.
Sounds good, thank you.
Okay, so just to wrap up the last tutorial that we did, the QwikMD one, just to clarify, QwikMD is just producing files and then calling NAMD, yes, the molecular dynamics engine, to do the simulation. So it's just a preparation tool and the analysis once you do the simulation. It's not the molecular dynamics program per se, QwikMD, but it uses the NAMD code. Okay. Okay, so let me share my screen. So the tutorial that we're gonna do now is called, so if you have here, let me share this page. Yeah, it's this one. So the page that you're seeing right now, you can access through I'm gonna put the link in the chat. And this is one of the free energy methods, free energy and enhanced sampling methods tutorial. So let's do that, at least the first part. So where's my, here. So let's run BMD. Yes, just please download the files. Here there's recorded files. So let's do that. let's move here. So in the folder, are you everyone ready? Already downloaded the tutorial files? So then if you go to the PDF here, I have it here. Okay, so the tutorial, if you see, is the same system that we did before, the peptide 10 alanine peptide, the decalanine. But now we are gonna do free energy using a different flavor of biasing simulations called adaptive biasing force, or ABF. So let's go. So we're gonna do the first part of the tutorial, which is the unfolding of the decalanine. Okay. This tutorial also has free energy by other methods, like I think this is a FEP, or free energy perturbation. So it has a little bit of everything, but let's do the first one right now. So let's go here. So here we have the folder. In the tutorial files, we have another folder called decalanine. If you go there, we have a PDB, a PSF, and a configuration file. Okay. So let's read out the tutorial. So the structure files and coordinate files, we can load them in BMD. It's BMD. So we can navigate towards the folder. In my case, is tutorial ABF decalanine. Okay. So I can load the files using the console. Let me that's a little bit bigger. So I do a mol load PSF, the name of the PSF, PDB. And that will load the system, which is the same system that we were working before. It's just a peptide. If you want, you can just make it a little bit nicer with I like the CPK representation, the drawing method. Maybe it's a little bit too much. Let's do a new cartoon. And then color ID. So this is exactly the same method, the same system that we had before. So the tutorial presents you with two different reaction coordinates. So basically, the process that we're gonna simulate is the unfolding or stretching of this peptide. But you can do it in many ways. So in the previous tutorial, what we did was to basically apply a pulling force to the full residue, the first residue, in a direction. So now we're going to do a similar biasing, but using the Colvar model. So it tells you a little bit about what the Colvar variable is and how we're going to do it in two different definitions. So it says that the two functional forms of the Colvar are the atom distance, which basically the atom distance corresponds to the interatomic distance between two groups, two atoms, for example. And the other one is the center of mass distance. And the center of mass distance corresponds to the separation between two groups of atoms. So let's continue. Now let's navigate to this to the tutorial document files, and let's go to the configuration file. Okay, so let's go to this abf.conf file. So this is the one that NumD is going to run, which again has the structure, the number of steps, parameters, and then all this is just the thermostat, the Langeron thermostat. Here's basically, if you remember that I showed you the configuration file for the SMD that had this keyword SMD on. So now instead of doing SMD on, we are doing Colvars on. So we are activating the module Colvars, and the only thing that we need to do is just this, Colvars on, and then the configuration of the Colvar is in this file distance.in, okay? Just as simple as that in the main config file. So let's go and look at this file, the distance.in. So this file here has a little bit more detail, but if you look at the detail of this file is actually written in the tutorial. So again, we have in the tutorial the same two instructions, the keywords Colvars on, and here we have the configuration of the file, or the content of the file configuration distance.in, okay? And what this file is telling us is that this is the definition of the collective variable. Okay, now we're gonna go over. Let me zoom in a little bit more, although we have it here. And then after that, we have basically the definition of the method, which we're gonna do, ABF. So it's relatively straightforward. So what is this collective variable? How is this defined? So we have the name of the collective variable. It's called atom distance, because then at the end we're gonna refer to, in the ABF part, we're gonna say, okay, apply ABF to this collective variable, which is called atom distance, okay? So the name is important. And then we have these parameters, width, lower boundary, upper boundary, that basically tell us, okay, this is the collective variable has values that goes from 12 to 32. And the spacing of this collective variable is 0.1 angstroms. And then the actual components of the collective variable can be specified in different ways. In this case, we are specifying a distance component for the collective variable that is basically telling us is the distance between the atom number 10, so one atom, and the atom number 92, which is one atom from the first residue, the one that we were pulling before, and one atom from the last residue, the one that was kept in place. Okay. So basically, we need to know the atoms, the atom number of each of the atoms that we want to measure this distance, and we are telling the module, okay, this distance is going from 12 to 32, or this is the space between 12 and 32. You can sample all this space.
Is 12 angstrom is the initial distance between those atoms?
Yes. So if we look at this structure at the beginning, right? How do you know the values to put here? So that's a good question. So you can go. Let's go back to the licorice, maybe. Okay. So if now I create another representation that is just index 10 and put it as van der Waals. Is this okay? Right. So just if you didn't realize before, the counting in NAMD, which is what we have here in this tutorial or in this file, is different from the counting in BMD. So in BMD, there is index 0, whereas in NAMD, the first atom is index 1. Okay, so basically, the atom here 10 is the index 9 here. So this is it's a little bit big, but that's fine. So this is the atom that I have here, the group 1, and the group 2 is the one that is called this 91. So it's this one. So now if you go to mouse, label bonds, you can measure the distance between these two. So clicking here, here. Okay, let me change the color of the background. Okay, so now we can see the distance between these two atoms. That is actually 13.73 angstroms. Can you see this a little bit small? Okay. So what it's saying, what we're telling here in the Colvar module is, I want to explore the free energy of this process, going from 12 angstroms, which is like a little bit shorter than the equilibrium distance. The equilibrium distance was 13. So we're going a little bit shorter, and then up to 32 angstroms, okay? Okay, so that means that at 12 angstroms, we are actually perturbating, like we're going against the equilibrium distance. So we expect to have like a higher free energy than the value here in equilibrium 30. Okay, so let's go back to the tutorial. So it says here that after showing this file with all these values, it says that the width of the collective variable is 0.1 angstroms. The Colvar has a range of allowed values from 12 to 32 angstroms, and the potentials, the boundary potentials that are defined here, the lower wall and the upper wall constant, is basically telling the systems, I force you to be between these two values with a force constant of 10 kcal per mole. Okay, you can change this force constant if you think it's not enough, and you see that the system starts to fluctuate, and this collective variable goes beyond the 12 to 32, you can increase the force constant.
It is not a spring constant, right? We're not like pulling here with a spring force. Or is it? I mean, like, what is boundary potential?
Boundary potentials mean like I'm preventing the system to go beyond the boundaries.
Mm-hmm.
Okay. If I go beyond the boundary, I apply a potential to the system. You can think about the similar way as SMD. So SMD will apply the potential, the force, during the whole simulation. In this case, it's only applied if I am outside of this, this part.
So this is kind of like delta function at the boundaries of the...
Yes.
Okay.
The difference between ABF and SMD is that SMD, you traverse the coordinate, the relation coordinate from the left to the right. Just goes like pull, 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 and then finish. ABF, the system is free, sort of a way, between these boundaries. So the system can go from one side to the other, go back and forth, back and forth. The only thing is that if you don't see the system populating the whole boundary, the whole 12 to 32, then what happens is that the method starts to bias the system so that it goes and populates the rest. Let's say that the peptide only stretches between 12 and 20, okay? Because then it's going farther from 20, it's like a lot of energy. So what happens is that ABF starts to collect sampling. So the simulation starts to go up. And then at some point, ABF says, wait, I'm collecting a lot of sampling, but I haven't been to this other part of the collective variable, to the 20 plus, 20 to 32. So at that point, ABF basically bias the simulation so that the system can go to that part, okay?
Mm-hmm. And this bias is specified by this bin width? Or?
Yes, and it's specified by the force constant, and it's specified by the force sample. So basically, what it's saying is that during my simulation, I need to sample enough of this collective variable along this part. Otherwise, my result will be bad. If I'm not sampling the whole part, the whole reaction coordinate, then my energy of that coordinate is going to be bad. I need to have a lot of sampling in all parts of my coordinate. Okay? So these values, the width of the collective variable, the force constant, and the force sample, are somewhat a trial and error process. So you need to define some values, check your simulation, check that the sampling is homogeneous along the whole reaction coordinate of the whole collective variable. And then once you have that, you can be sure that your free energy, which is the result of this simulation, is correct. Okay. But if you compare ABF again, if you compare ABF with SMD, ABF is more flexible in a sense. And that gives you smaller forces and usually better convergence than SMD, usually. Okay, so the tutorial also presents you with a different Colvar, so you can compare the simulations between the two Colvars. We said that the first Colvar was defined by, it was called atom distance and was defined by a distance component, which was the difference between atom 10 and atom 92. The next one is called center of mass distance, or com distance. And now it's defined by a component distance, but now each group has 2 atoms, okay? And these 2 atoms basically have, what we are doing is having the distance between the center of mass of atom 4 and 5 and atoms 99 and 100, okay? And then the ABF method is very similar. We just say, apply ABF to the Colvar that is now named com distance, and the same, in this case, the same 4 samples. So let's go to look at the results files, okay? That they're already prepared in the file, in the folder of the simulation. So we are here in my tutorial files, and so before that, how will you run the simulation? So just to run the simulation, you need to be able to do, you can call NumD, and the configuration file, which in this case is this one, com file. Just check that NumD is installed. You can do NumD, and it will tell you I'm running, but no simulation config file was specified. Okay, so NumD was running, but I didn't say anything. So let me clear and run NumD with this ABF. Let me check how many steps is this. Okay, so let me just run the simulation and then stop it, okay? So you can do this later. So I run the simulation by doing NumD, the config file, and then I send this to the log file. So I just call it abf.log, okay? So if I do the ampersand, then I run this process in the background. I'm running in Linux. So I run this. What the error in the collective variable? Okay, that's good. See what happens. Let's see. Okay, so let's read from the very beginning. Okay, so here it says, I'm running Colvars, initializing the collective variables module. Please cite this paper. So I'm reading the instance in file, which has these values, initializing a new collective variable called name atom distance, which has a new distance component. This is fine. Atom group 1 is defined with 1 atoms. This is fine. Total mass 12. It's 1 carbon. Group 2, the same, another carbon. Okay, so it says reading legacy options, lower wall and lower wall constant. Consider using a harmonic wall restraint. Okay, so this tutorial is outdated. The value of lower wall must be set explicitly. Okay, so let's do that. So basically what we need to do is we need to change in the file distance. Instead of calling it lower boundary, we need to call it lower wall, I think. So let's call it lower wall and upper wall. Okay? Let's save this file. Everyone is following so far?
Yes.
Okay, so let me see if I run the simulation again and I know, call it log2 or ABF2 cloud. Nope, that's the problem. As you see, this is sometimes the errors in NumD are very informative. So you can go and check. So it says user control feature upper boundary cannot be enabled automatically in Colvar atom distance. Try setting it manually. Okay, so it was not a problem of lower wall, and let's go back to boundary. And just put lower wall. And upper wall. See if the third time is a charm. Okay, now it's running. There were some, since this tutorial is a little bit old, the Colvar's module has been updated to now ask specifically for the variable lower wall and upper wall, which is basically just the same thing, the boundaries of the Colvar. But if you don't put these values in the new version of NumD, it just complains. But luckily it tells you you're missing this variable, so that's fine. Okay, so let's see how it's going. So this is the output file of NumD. So you see it says collective variable initialize 1. And now it says initializing a new ABF instance. So now that we define the ABF, is we define the collective variable within the ABF. Okay, so it looks like it's running. Yeah, it's running. Let's go back to the end. Still running, still running. Okay, so let's just stop the simulation. Okay, so you can do that by going back to finding the process ID. That's this one in top. And just type in Q. So that finished now. And now let's use the output that is provided in for the tutorial that is in the folder called example output. Okay, so let's go to the example output. let's imagine we already finished with the simulation, that it shouldn't be long, but just in case. And then we can see here that there are a few files, not all the files that were produced by the simulation, but let's go back to the tutorial. So it says, so far everyone is following?
Yes.
So the tutorial now, section 1.3 says ABF produces the following output files. It says we have the .grad file, which estimates the free energy gradient, and the count, which is a histogram of samples collected. We have the PMF, which is actually the integrated free energy profile or potential admin force, PMF. So let's continue actually. So the data is in text format. It can be read with any plain text editor and plotted with a variety of software. So let's plot this for the two collective variables. Remember, there was one that was just separating two atoms, and then the other one that was separating two groups of atoms. And let's see if there was any difference. So we can do that. Let's plot that. So we have here in this folder the files called PMF. So let me visualize this file, the ABF000 PMF, and see what happens. Just two columns of data. The first one is the collective variable or reaction coordinate, and this one is the potential admin force of that collective variable. So we can plot this one using any software. I'm going to use GNU plot. Okay. No, I don't have GNU plot. Why is it working? Do I have Excel in this? Do I have Excel? I have the open office. That's fine. You can do it with GNU plot if you have it. Okay, so I'm going to open each file. I think if I do open, it should work. So let's navigate towards the tutorial, ABF, decalanine example. And here I have the PMF. So it's gonna, since this is text, it's gonna import it as separated by tab. I think this is fine.
You can add a space.
Okay. Or I can do data, text to columns, which is the same space. Let's do fixed width. Just click here. Okay, so we have the first column and the second column here. So if we plot these ones, chart, scatter, finish.
May I ask, you usually don't use Excel for plotting, right?
Myself, I actually use Excel for plotting. I think it's pretty powerful.
Okay.
In this computer, I don't have Excel because I think it's just a computer I started working with since the pandemic, as in my home. So.
Okay.
But actually, I use Excel. I like it because it just, you can keep different tabs for different projects, and I think it's well organized. You can use whatever. So let's load the other file. This one was the 0 file. File open. The 1. And this was fixed with. Let's put it here again. That's fine. So now let's bring this column to the other file. Put it here. So let's add insert. Oh. Let's add a column. So now this is the C2 to C2. Okay, so we have the plot for the two collective variables. This is actually the free energy. If you look at the tutorial, it's the same plot. Okay. Okay, so any questions so far?
May I ask, when you run this ABF, it is kind of like sequential process, not like umbrella sampling when you have running different windows at the same time?
No, right. You can do both. You can do ABF in different windows.
Ah, okay.
But this is like, the example that we did is just one window, one big window from 12 to 32.
Mm-hmm.
And as I said, ABF just samples.
Mm-hmm.
And then whenever it's happy, just stops.
Mm-hmm.
Yeah, in a real life, work, you will do different windows, small windows for ABF, because you can run all these windows concurrently at the same time. And that's like speed ups the simulation quite a lot.
Mm-hmm.
So let's say we could have done several simulations, each where we ask for the collective variable to be only between, let's say, 12 to 14, 14 to 16, and so on and so forth. And then we'll have like several simulations running at the same time.
Mm-hmm.
So yeah, that's ABF and a little bit of collective variables. If you want, we're not gonna cover much of this, but if you wanna continue doing this on your own time, or maybe next week, or whenever you have time, you can see all the powerful things you can do with collective variables and ABF as well.
May I ask, if you do several windows, how does the program find the initial and final step for the window? You mean like the structure, the end structures?
You mean like at the end, once you finish all the simulations, how you go back?
No, like if you have several windows and you want them to run at the same time, you need like, for example, if we split this like a 20 angstrom window into like 4 windows, and we want to run them in the same time. But before we start running them, we need initial structure for each of this window.
Yes, that's a good question. So the thing, usually what you do is you do first an SMD.
Uh-huh. Okay.
And then from the SMD, you take the values, the structures there, because you only need a rough estimate of the initial structure
Okay.
for the window. That's how you do it. You do an SMD, for example, and then you take from the trajectory, okay, let's take this when the distance is 20, and then I take the structure and I prepare a window. When the distance is 25, and so on and so forth.
Okay, thanks.
Okay, so if you're interested in the possibilities of Colvars, you can go to NAMD user guide Colvars, probably. So if you go to contents, there is a chapter of collective variables here. And everything you can do with collective variables. It might be a little bit overwhelming at the beginning, but I'd say that it's very, very, very powerful. So if you go here, you can see all the different components that you can get, like for example, distances, angles, contacts, rotations. You can do collective variables with RMSD. And collective variables later on allows you to do almost every free energy calculation that you want to do. So I would suggest, if you're interested in doing free energy calculations in NAMD, you spend some time learning collective variables. Okay, so let's stop right now with this tutorial. Is there any questions?
Is there any significant overhead for using collective variables in terms of performance?
I would say no. It is true that collective variables is, you may say, is like a separate module that it was incorporated into NAMD, but it's, if you're running simulations with your CPU or in a cluster with a lot of CPUs, supercomputer, collective variables is not very demanding. It is true that if you want to run the new NAMD GPU resident version, the 3.0, then the collective variables can be a little bit problematic, because collective variables at this point is not GPU resident. So basically, if you remember Julius talking about that, now NAMD 3.0 does everything in the GPU. Well, actually, collective variables is not in the GPU. So but that's something that you can talk to Mohammed maybe. Mohammed, you were thinking about doing collective variables in GPU, right?
Yeah, but I'm not sure if it has been merged to NAMD 3 yet. Usually, the way that Colvars works is that at every steps we need to collect some information regarding the atom distance and the force on the atoms. So if you're using the NAMD multi-core version, which is basically running on the CPU, you wouldn't see much difference. But when you're using the new GPU called NAMD 3, all the information exists in the device, in the GPU device. And in order to get those information, you have to copy all those data back to your CPU and then give it to Colvar to do the analysis. And then Colvar will return, if there's a bias, it will return a force that needs to be applied to those atoms. And then now you have to again copy back to GPU. And that would be basically a bottleneck for the NAMD 3 performance. But if you're,
correct?
Can you repeat again?
That has to be done every step, right?
It has to be done at least. I cannot, sorry, hear you well.
So I'm sorry, give me 1 second. So the collective variables have to be evaluated at every simulation step. Is that correct?
You can, and also there is an option in Colvars that you can specify how often you want to do the calculation. So you can also set it to do it every, I don't know, 10 steps, every 20 steps, 100.
But will that not, so you're introducing, let's say you have a harmonic spring potential between two atoms.
It's depending your spring constant. If it's very stiff string, yeah, you're gonna basically your spring will fluctuate a lot, and you need to use you need to basically calculate this Colvar's every steps. But if you have very loose spring and the mass of your atom is not too light, then you can get away by doing this calculation every other steps, or maybe every 10 steps.
Right. So it's basically trial and error, sort of.
Yeah. I mean, if you're running on the CPU, I don't think
I can understand how doing.
If you're doing on a
Yes.
CPU, there is no, like, payoff. You're not going to lose much performance by doing every single steps Colvar's calculation.
Right. Yeah, I can understand how NAMD 3, if you want to do everything on GPU, that it might be difficult. But if we don't calculate the collective variables every step, then for
yes,
some
that's
cases,
a discussion that we are having actually right now. What's the merit of having collective variables being calculated every time step? And if it's possible to do like sort of like multiple time step collective variable, but actually it hasn't been proven that it works if you do that. I mean, it's a possibility. You need to prove it, basically.
You can basically calculate your relaxation time. If you remember from my slides, I show you the tau value, which is a function of the mass that you have, and also your spring constant. You can calculate the relaxation time, and the relaxation time needs to be more than your simulation time steps. So if you're doing 1 femtosecond time steps and you're skipping 10 steps before doing another Colvar's calculation, so we are talking about 10 femtosecond, and your relaxation time needs to be more than that. Otherwise, you will see this oscillation effect in your simulation. You see resonance effect in your MD, and your simulation might be unstable after that.
Thank you.
You're welcome.
Okay, so let's continue. We have still almost an hour. So let's see how many people would like to go over the force field toolkit tutorial. Just raise your hands or sign, just say yes or no.
How do you raise your hand?
I don't know.
Okay, I just said yes.
Okay.
Click on the participants and you see raise your hand.
Okay, Amna, you said not yet. Are you still working on this APF tutorial or? Okay. So how many people are interested in quantum chemical simulations? Just like outside of NAMD. So just, or to routinely do quantum chemical calculations. Okay, 7. Okay, so let's do like a small survey. So which software do you use? Do you use, for example, Gaussian,
Orca?
Orca? Do you do, perhaps there are people from material science that do VASP or Crystal or Siesta or CPMD. No? Mostly Gaussian and Orca. There's also GAINS, QChem, TeraChem, NWChem. Okay, so I can show you a new plugin that we are working with. We're working on for quantum chemical simulations. It's on the alpha, not even alpha, it's gonna be released. Actually, it's already released if you downloaded the latest VMD alpha that is in the website. It's there, it's called QM Tools. The idea is to have like a QwikMD, the same idea of QwikMD, but for quantum chemical simulations. So basically, we want to be able to assist the user in preparing the simulation, setting up the molecule, preparing the simulation, and then analyzing the results. Okay. So while we wait for just in 5 minutes, I can show you the plugin. So let's open PMD. There is no tutorial for this plugin because it's still on development. But the idea is that even though it's very simple, I'm gonna create a tutorial maybe in the next couple of weeks. So you can go back to the tutorial website or follow me on Twitter or follow the group on Twitter. And learn a little bit more maybe. So if you go to extensions, simulation, and right next to QwikMD is QM Tool. Okay. So the idea is that QM Tool, as I said, it's a very preliminary version. But So what you can do, for example, is go to Molefacture. Remember Molefacture that I presented this morning? Okay, so you can open Molefacture and create a molecule. Let's say I want to run a simulation for I don't know, acetaminophen. Remember so let's do new molecule from scratch. So let's go add independent fragment. So if I remember correctly, acetaminophen had a phenyl group. So let's put a benzene, okay? So then here on one side, it had a hydroxyl. So let's do build, replace atom, hydroxyl. There you go. If you want, you can follow along because this is actually, this will be the first part of the FFTK tutorial. The first part of the FFTK tutorial is actually creating the molecule that you want to simulate, the one parameters. So let's do that. Let's open Molefacture and create acetaminophen. Okay. Sorry if I'm butchering the word. I really don't know how it's pronounced. I think it's acetaminophen. Okay, so I did add independent fragment, benzene. Then I click on the hydrogen that was here, and I did build replace with hydroxyl. Okay. So now let's do the other part of the molecule. If I remember correctly, there was a nitrogen here. So let's change the element to nitrogen. Then we can do this, we can use this feature, which is the autocomplete hydrogens. So here, since this is a single bond for Molefacture, if I do add hydrogens, it will create two hydrogens here. You see? So one of the hydrogens is actually the one that we want, but the next hydrogen we need to replace by an acetyl fragment, which I probably don't have here in the library of Molefacture, but I can create. So this is, let's think a little bit. So I can do it step by step. So I can go like methyl, and then, so this would be a oxygen. So now I can change this bond. So if I select both atoms here, I can change the bond order from single to double. So I put a double bond here. And then the only thing that rests is just replace this hydrogen here with the methyl. That's it. Right? Is that acetaminophen? Of course, it's just very badly. There are a lot of clashes there, but we can deal with that. Just go very quickly. Yes. So let's show the quick minimizer of in action, actually. So let's minimize this because this is very, I mean, I don't know, maybe it's not that bad, but it looks very bad. So let's minimize it. So let's minimize using universal force field, OpenBabel. Oh, I don't think I have OpenBabel. Let's use NAMD. So let's minimize 500 steps.
Sorry, how do you choose two atoms at the same time on the structure?
You click and hold. You hold Shift and click the
Okay.
two atoms.
Okay.
Just click one and Shift and click the other. You can do the same in the table here. Like one and Control and the other. Let's try. I don't have the open bay. So let's try. Oh, here, error. Unable to find bond parameters. Right, because I didn't set up the atom types. So let's do that. So the carbons in the ring yeah, this is probably not the best. Okay, let's keep this minimizer because I don't have the parameters for this molecule actually because I just built. So, but let's export this to QM tool. Okay, so what we do is let's file. Let's close QM tool and to file export to QM tool. Okay, so now I have this molecule in QM tool and manufacture is closed. Okay. Is there any questions so far? Are you following along? Okay, so what we can do with QM tool is prepare a simulation, and I want to prepare a geometry optimization because this geometry is very bad. So let's do that. Let's go to define QM input, and here we have several options. So we can select the software that we want to use. I don't have Gaussian installed, so let's use Orca. I think I have Orca installed. And do a geometry optimization. I go to simulation type, geometry optimization. Let's do 4 processors. This is a neutral compound, so the charge is 0. I think it's a singlet, so multiplicity 1. And let's do a method. Let's do a bit relief density functional theory with a basic set of 631G. Okay, so this is a typical simulation that you may do. And you can do file, write, and let me go to test, and let me create this, call it acetaminophen. Okay. So for those of you familiar with Orca, let me go back here and let's go test. So now I have this file acetaminophen. Let's look at it. So it looks, I mean, like any other quantum chemistry, there is a section where you have the coordinates, and then there is a section where we have just the information of the method. Okay. So now we can do is, I think I have all kinds of. Yes. Or yes, I have an org installed. So let me run the simulation. And let's see the outputs. Okay, for parallel runs, Orca has to be called with the full path name. That's fine. So the full path name is this one. So let's call it with the full path name. So the input, and then I want to put this into the log file. Let's call it out. Okay, let me change the input. Remove this part, which is the one that controls how many processors I use. So let's try again. Now it's running. So now I'm running a geometry optimization with Orca. This is not NAMD. This is not molecular dynamics. This is a quantum chemistry. And it will take maybe a couple of minutes, 5–10 minutes. While we do it, we just leave this in the background. And let's go back to QM tools. So let's actually do the following. Let's just close QM tools, remove this module, and we can start the FFTK tutorial. Is that okay?
Sorry, how if you have like a big protein molecule and you want to do QMMM hybrid, like you want to treat some part, like especially the active site with QMM with QM, and the rest of the protein with MM, can you do it in this QM tool?
At this point, no. You can do that in QwikMD.
Okay.
In QwikMD, the plugin that we showed earlier today.
Okay.
Let me show you.
Okay.
Let me show you. QwikMD.
Okay.
Okay. So in advanced runs here, you have the option to do QMMM. So if you're interested in QMMM, in the hybrid QMMM, I would suggest you go and check QwikMD, because this is the way I learn about QMMM myself. So I think it's a very good thing. So you can do the QwikMD tutorial as we did, just to understand a little bit about preparation, and then do the QMMM tutorial. There's a QMMM tutorial in the website, which uses QwikMD. So if you go to the tutorial page and look for QM, you can also do, if you search in Google NAMD QMMM, it goes to the website of QMMM. And at some point here, there is a lot of text explaining the method, which is nice. Here there is tutorial. So the tutorial is this one. And the tutorial is rather short. It's only 16 pages. And you see, it uses QwikMD. Okay? It tells you how to select the parts that you want to treat quantum mechanically, and the rest is treated classically. Okay? The QM tool, on the other hand, is just for purely quantum chemical simulations, quantum mechanics. And I show you how to prepare the simulation, but that's not really the main point of the QM tool. The main point is to use the plugin to analyze the simulations, which is something that maybe the quantum chemistry community doesn't have right now for every program. And BMD is very powerful. Just you saw the really nice figures that Rafael showed for the QMM, all these beautiful orbitals. And you can plot those in QM tool as well. Okay, so let's do the tutorial for the force field, the parameterization tutorial, okay? Or at least just a part of it. So if you go to the tutorial page and you search for FFTK, it's this one. I just saw you the message push out. Yes, you can force the amide group into planar. I didn't do that. Okay, so let's go. Instructions. Are we, those who are following, are you in the right PDF file?
Yes.
Yes.
Okay. Let me see if the simulation of acetaminophen has finished. How many steps? You did 5 optimization steps. Because if you remember, one of the first steps of FFTK is actually optimizing the geometry. So I was thinking that maybe we can parameterize acetaminophen instead of the one that is in the tutorial, which is ethanol. In any case, let's start the tutorial. So the first part is just a very similar explanation of the force field and what are the terms that are actually parameters, as if you remember my presentation. We have the workflow. Okay, so one caveat from this tutorial is that this tutorial used the old version of Molefacture, not the one that I show you today. Okay, so the instructions here in the tutorial are for people that has the BMD 1.93, I believe. If you have BMD 1.93 and you open Molefacture, you will see this plugin instead of the one that I showed you today. Okay? It's a little bit different, but so if you have BMD 1.93, you can follow this tutorial as it is. If you have the latest version of BMD, the 1.94, then you can do what we did, let's go and open Molefacture, and let's create a molecule. Okay. So let me close PMD because it's not responding. Let me open it again. And let's open. Has everyone opened Molefacture? Okay. So let's create a simpler molecule. Let's create ethanol. Okay. So for ethanol, we can go and do methane and replace one of the hydrogens with another methyl. Okay. And then replace this hydrogen here with a hydroxyl. And then we have ethanol. So are you following?
Sorry, could you repeat, how do you add this molecule?
So this one, what I did is let's go again. So new molecule from scratch, okay? So I did build, add independent fragment.
Okay.
And then I select methyl or methane. And then I started building the molecule like piece by piece. So for the ethanol, we go from methane to ethane. So we just replace hydrogen with methyl. So now we have ethane, okay? And then we need to add the hydroxy group. So we do replace hydroxy. And that's it. Okay. Now let's go to the tutorial. One second. So the tutorial suggests you to assign these atomic properties for the ethanol, because that way you will match the van der Waals parameters much more easily. So let's do that. Let's do that here. So we have the table here, and let's fill these values here. So it may take a little bit, but it's like we have C1, CG331, H11, H12, H13, C2, C21, C22, O2, H2. These are the atom types for the general force field for most of the carbohydrates and organic molecules.
If you would create another molecule from scratch, how will we know that we need to change to these atom types?
So what you should do is well, in principle, if you're gonna parameterize, you can try to match your structure with similar structures. In this case, we are having, so what is this atom type means? The CG331 is this atom here. This atom is a methyl that has, it's a methyl from it's a carbon from methyl. So it has three hydrogens. That's why the nomenclature 331. So every time we have a carbon that is a methyl, we should use this CG331 atom type. Okay. If you go to the topology or parameter file of any molecule that may be similar to the one that you have, that has the same substituents or let's say the same side chain, you can use those atom types in your molecule.
BMD couldn't recognize it by itself. How many hydrogens are connected to carbon?
Yes. I personally don't know by, I don't memorize these atom types. I just, every time I see, okay, this methyl, I know methyl is somewhere, I look at it and that's what I find.
Okay.
So I think that's fine. So now we need to write the PSF and PDB once we have these atom types. So let's do that. File, write PSF and PDB. Okay. Let me try. Let's go to the test folder. And I have one called F50K. So yeah, let's put it here. So this is, let me call it new ethanol. And yeah, BMD crashed. Let me try again. Or let's skip this part and let's go and use the tutorial files. Okay. So let's so here are the tutorial files. Let me just go and pick the PSF and the PDB, the topology. Or just download everything. Everything is faster. So let's download this. I think I already have it, but just in case. So let me still running simulation. Yep, let's do it again. Just more in the files so that it doesn't. Okay. Do you have the files? Did you manage to get the files? So we did the constructing the small molecule with manufacturing. So the first thing that FFTK does is to create the parameter file. So let's do that. So we go to modeling force field toolkit. There you go. And so the first tab is the one that builds the parameter file, and then everything else is gonna basically populate that parameter file. Remember when I presented the parameter file that had the bond, angle, dihedral sections, where you have the values for each bond, the two atom types, and the value, the first constant, and so on and so forth. So the parameter file is the one that says, okay, I have all these bonds, angles, and dihedrals with these atom types and these force constants and everything. So let's do that. So navigate to the build part tab, so we are here, and expand the identify missing parameters. So what we need to do is to place the PDSF and the PDB, okay, and click analyze. So let's do that. So let's navigate to the place where you put your tutorial files. So example files, in my case, system prep. So this is the PSF. The PDB should be here. These will be the files that were created when manufactured. So let's do analyze. And the analyze will say, okay, we have these bonds, carbon, hydrogen, carbon, 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 hydrogen, these angles and so on. And let's save this file. So let's click here. And let's go to the working directory here and write parameter 0. So the first the parameter file. Let's write the file, okay? So if you go to the directory, that is the working directory where I put the file, and let's look at the file. This part 0. So there is a lot of text, but at the end, the section that is the bonds, you see, the atom types are correct, but the parameters are 0. So they are not there yet, okay? So what we did is only to create the template, okay, that then we are gonna populate. We're gonna find these values and we're gonna put them here, okay? So let's do that. Oh, let me show you another thing, the parameter file. At the very end, so we have angle, dihedrals, impropers. At the very end, we have the non-bonded or Lennard-Jones parameters. And these are, as I said during the talk, these are not set in FFTK, meaning that we are not using quantum mechanical simulations for these parameters. What we do with these parameters is just set them by analogy. And this is the first part of the tutorial. So let's read the tutorial. So in the number 6, the item 6, it says navigate to the build part tab. We're here. and expand the assigned missing van der Waals general Jones parameters by analogy. So we expand this one, which is, we can close this one or minimize this one and expand the second one. And now it asks us to browse and complete the parameter file. We can load the parameter file. And now we have the, if you look at it side by side with the actual file and the GUI, the FFTK GUI, we have the parameter files, the values of the epsilon and r min that are in this file, okay? Here in this table. And we're gonna populate those. How? We're gonna set from reference, but the first thing we need to do, let's read the tutorial. So use the browse button to specify the in-progress parameter file. We already did that. And click load. We did that. Second, load the CGNFF topology and parameter files here. So we're gonna go load topology and parameters. And we are gonna navigate towards the sample files, the common part. And we have the topology and the parameters. And now we have parameters and topology for all the atoms. So what we're gonna do is we're gonna select the first one, which is the carbon CG321, and we're gonna filter by element. We're gonna go carbon, and we're gonna go and find the CG321 here. And it says, the comment says aliphatic carbon CH2, which is exactly what we want. So then we just click set from reference. Okay. So the advantage of setting up the types, the atom types at the beginning was that now we only need to match the atom type that we know with the one that is in the general force field. Okay. Any questions so far?
This reference parameters, does it contain all the possible atoms?
No, only those that are the most common ones. As I said, okay. For example, if here we have the CH2 atoms, the CH3, for example, here the CH3 is this one, methyl. We have this one, for example, CG334 is a CH3 that is adjacent to a positive nitrogen, okay? So most of the atom types that you can encounter are there, but not all of them. I would say that most of the carbon atom types, oxygen, nitrogen, are there, but not all of them.
What if you come in a situation that you don't have the atom type that you want to parameterize? How will you do? How will you go about that?
So what I would do is, for the van der Waals parameters, I would use a similar atom type. Okay, so I would use the parameters of a similar structure, if that makes sense. Because, as I said, FFTK doesn't generate these parameters.
Okay.
Is that okay?
Yeah, it's okay. Thank you very much.
Okay, so I will go ahead and do this. Select the second carbon and do this one with this carbon. So I match this. So I set from reference. You do the same for the hydrogen and navigate towards this atom type HGA2, which is here, set. The HCH3 is here. I'm doing this fast, but you can take your time. And the oxygen is this one, the hydroxyl oxygen for methanol and ethanol. So once you have these, then you can do update file. So you update file, and basically, let me go out and open it again. And you can see that now the values are populated for this part. You see? So basically, just rewrite the parameter. And okay, so the next step would be to start parameterizing all the other terms of the force field. The first one is the water interaction, which deals with the charges for the electrostatic part of the force field. Then we have the force constant for the bonds, and the angles, they are done together. And then the torsions for the dihedrals. Okay. If you're working with a molecule that is somewhat common, what you can do is to use the CGNFF web server to get your parameters, okay? Not every time you need to go and do this from scratch. You can use what has been done previously, okay? So let me show you how to do that, because it was a question that was popping up in Slack. So the CGNFF web server is a website that from the group of Alexander McCarroll. I think here, yes. So the website is cgnff.umaryland.edu. So why is this? Is the people that develop the Charm force field? Okay, so the Charm force field is continuously updated with new information about atom types and parameters. So that means that sometimes you're working with a molecule that might be already solved or that might be already parameterized. So the first thing you should do is to check this website and submit your molecule, okay? And the website will tell you, okay, your molecule has these parameters, and for each parameter, it will tell you there is a penalty associated. If the molecule is rather, what? Oh, okay. So what I did is just I click here and it took some time, but I opened the window again. So let's do that. Let's upload a molecule. I'm just curious about the geometry optimization. Let's just still going. Let's upload the molecule. For this web server, you need to register an account. So I have my account, I think, yes. But you can do this, it's free. It's just to keep track of the users, okay? So you can go to my account, register, and follow up this questionnaire. I have my account, so let's log in. And you can choose a file. So what you need to provide is basically either a PDB or a MOL2 file. MOL2 is a different file format that you can create. But let's just do the PDB. I think it should work. So let's do choose file, and let's go to my home, test, new FFTK. And the tutorial files I was working with, I'm finding the PDB. Okay. So if you upload a file, I made a mistake. Let me go back again. So when you need to upload the file and tell them to give you the parameters that are already in the force field. So if they are already in the force field, I want to know them and I want to have them. Okay. So let's do that. Okay. Yeah, it's complaining because I'm not using a MOL2 file. So let's use a MOL2 file. Please upload your molecule and MOL2 file. Okay. MOL2 file. So let me just, I have the MOL2 file now here. So just give me a MOL2 file and I just, okay. I have this MOL2 file here, or you can create a MOL2 file in Molefacture. Let me show you how to create a MOL2 file in Molefacture. So if you go to new molecule from selection and you choose all, so basically you have the molecule that was present in BMD. Okay. So now you can do is file, write MOL2 file, and it just gives you a MOL2 file. Let's put the MOL2 file here. And that should give me the MOL2 file. Let's see. Yeah, this is the ethanol MOL2 file. So let's close Molefacture. It did its job, yes. And now let's go back to this web server and upload a new file. And this time, let's upload the MOL2 file because it was complaining. So here, give me the parameters from the force field. Okay, so now the web server returns this string file. Let's open it. Okay, so this says topology and parameter file combined in one. That's a string file. And it has That was generated by the Charm General Force Field CGNFF program. It says penalty is the highest penalty score of the associated parameters. Penalty is lower than 10 indicates the analogy is fair. So you can use those parameters without any problem. Penalties between 10 and 50 means some basic validation is recommended. Penalties higher than 50 indicates poor analogy. And these are basically, from now on, you say, okay, these parameters are good, you can use them. Or they are bad, and you need to re-parameterize those. Does it make sense? Since this molecule was fairly simple, it was ethanol, and we basically just used the atom types that were already there. All these penalties are zero, meaning that I don't need to reparameterize ethanol for my work. I can use the force field. Okay? So one thing you can do is just save this file and use it in your simulation. So let's save it. Ethanol STR. So let me save it. Save. Okay. But let's imagine that we don't have ethanol and we have another molecule. Then we need to go to FFTK and do the process. Okay? Does it make sense?
Yes. Is there a simple way to parameterize those halogen bonds, like bromide?
That is something that is gonna be available soon. Yes. It's not right now. I don't think it's in this version of FFTK, the one that you have available right now. But it's actually something that has been developed like a couple of months ago, and it's still in testing process, and it's gonna be available probably by the next PMD alpha release, probably next month or something like that, if it's not available yet. Let me try. So let's do this, and then we can finish, because we are almost at the time so let's try a molecule that has a halogen, okay? So let's do this. Let me open manufacture again. Let me close the 50K. I'm not gonna use it anymore. Very small picture. Let me go back to PMB. I'm gonna load again the files that I had before. So the PSF and the PAD. Okay, so I have this here. And now let's try to open Modefactor. Okay. So what I want to do is I want to use this molecule that is here. So let's do new molecule from selection. Let's do all. So all the atoms here. And let's get this molecule here. So now let's change one atom. So let's change, let's say this hydrogen or this hydrogen. And we change it for bromine, okay? And now let's write a mol2 file. So let's write a mol2 file for this, which is, I will call it Bretan, okay? And let's go to the web server and load this file that now has a bromine. And see what happens. Okay, it gives me a str file. And let's see. So you see now the penalties are different. They are not 0 anymore. And I would expect that the bromine has a lone pair. You see here? There is another particle in the topology file. So now we have a lone pair, which is collinear, is one of the types of lone pairs, called LP1, that is in the axis of the bromine and carbon atom. So the new charm force field recognizes the bromine and adds a lone pair to that. So now what we need to do is to parameterize the molecule around the lone pair. Okay, and for that we need to wait for the new FFTK version, which I will try to prepare a tutorial for this part because I bet it's gonna be a little bit more difficult than the regular water interaction part. Okay.
Could you repeat what is left to be done?
So for the normal ethanol molecule, yes, we need to go over all the steps in the force field toolkit. In this case, for the bromine compound, we will need to do all the steps, and in the step for the charges, we will need to do it a little bit different, okay? But that's not ready yet. So we need to wait for the next release, at least for the release of the publication that I mentioned earlier, okay? Which is almost ready.
Right. So this this file that CGen FF generated, is that not usable in Charm directly? And
yes, you can use it. Yes. So if you want, you can. Let's say this molecule is your drug of interest. You can create the multi file, go to the CGen FF web server, create this file, the str, and then use this str file in the NAMD input, in the configuration file.
Right.
Okay, and it will give you somewhat good results because I mean, you can say the charge penalty is fine; it's not that bad. And here you have the lone pair. I forgot to mention. This is the lone pair that has charge 0.05. I think during the lecture I said that the charge was 0.5. It's 0.05. Okay?
Right.
So this is the extra particle, the lone pair, and this is the distance between the bromine and the lone pair. Yes, you can use this file actually, the one that CGNFF gives you, in your simulation without doing anything else. For this molecule, which is relatively simple, I would say it's correct. Okay.
Okay.
Okay, so we are almost at 6 p.m. Central, which is already late. So I have.
Mariano, do you mind if I add one point?
Mm-hmm.
So when you create your molecule, if you notice, in order to run the simulation, you need to define atom type. And it's very difficult because if you look at the force field, different functional group, even it's like a carbon, it's depend if it's a neighboring atom is oxygen or you have a double bond, you have different parameter. So what is Charm General Force Field does is that based on the bond distance and atom type, is try to guess what is that functional group is. And it'll look at to the force field and trying to find the right atom type for that. If it's very confident that this functional group is, this is what it thinks, it give you a lower score. But if highly doubted that might be wrong, it give you the higher score. And that means basically it failed to detect what is the atom type is. That's why you have to go and reparameterize it. Usually this process will take a long time. You know, if even you look at the charm force field and you're trying to have, even for the simple molecule, you need to look through around thousands of lines to find out what is the right atom type and find the bond parameter for that atom type and the neighboring bond. And then you have to do it for angle, dihedral, and much more. This would basically make your life much, much easier without making any mistakes. Does that make sense?
Yeah, thank you. So so do you think the parameter file that CGNFF created is so that probably doesn't have the latest alpha whole thing, right? It's just, or does it have the I mean, it's, you said there was a lone pair, right? So
yeah, it has.
What it lacks is probably the correct angle and dihedral, etc. Those things. Is that what it would lack? I'm trying to understand what FFTK will have in 2 months that this current CGNFF force field doesn't already have.
Yes. So the paper that I'm kind of like mentioning and trying to sell, if you want, is going to show you that if you use the general force field that comes from the CGNFF observer, there's still some problems with that, because as Mohammed pointed out, this is due by analysis of similar structures, okay? So let's say when Makeras group, the CGNFF group, developed this force field, they did the work they did for these parameters is based on aromatic substituted compounds. So they did chlorobenzene, bromobenzene, and so on and so forth, okay? And they did that and they got a parameter for that. But if you do anything else that is different from that, something a little bit more complicated, they will give you some parameters, but they will fail. And in some cases, it will fail very bad. So this publication that I'm telling you is gonna be soon. It's gonna show you that if you compare the simulation with the CGNFF parameter and the one that FFTK is reparameterized, you get much better results with the new reparameterized parameter. That's what I'm saying. Okay. For most, I would say for most users, with the CGNFF web server, what it gives you, that's good. That's enough, and you can go ahead and continue your work. But if you have a compound that is not similar to what the database of the CGNFF web server has, so that the penalties are somewhat higher, then you better do a good job validating those parameters. That's what I'm saying.
Okay. Thank you.
Okay, and with that, I think we can close this session, and this is the last day of the workshop, so the survivors of the workshop are here, and we can say
We can say well done.
Thank you for having us.
Thank you.
Hopefully you learned a lot and you enjoy it.
Thank you
Thanks
very
a
much.
lot.
Thank you very much.
Thank you.
Thank you.
You can always contact us later on the BMD and the NAMD list, or send us an email to our addresses. Don't forget to yeah, so I'm speechless. Go ahead, Mohammed, say your last words. And then...
Nothing, just I hope you guys learned something new, and maybe we could convince you to use the awesome tools that Mariano or John or Ahmad explain, and hopefully you give a try to the new NAMD 3 on GPU. It's pretty fast. It doesn't have all the features, but if you're doing a regular simulation without using Colvars or fixed atom, you definitely want to give it a shot. It's pretty amazing. It's pretty fast. And let us know if you have any question.
I have a quick question. I was wondering if the recordings from especially day 2 are going to be available, are already available, or?
What I'm seeing from Google Doc, day 3 is available. Day 2 is also available, but I don't see anything for second section from 2 to 3. I can.
Well, it does take time to upload. I'm still uploading from home. All
uploading.
The videos.
Okay.
The afternoon sessions are much longer, so they're uploading and processing. That's why they're not available. I was talking to Rosita. Hopefully by tomorrow afternoon, all of the sessions will be uploaded and available.
Okay. Thank you. Thank you so much. Appreciate
No problem.
it.
You're welcome.
Okay, well, see you guys around.
Bye-bye.
Bye.
Bye.
Thank you very much. Bye-bye.
Thanks. Bye.
Thank you.
Bye.